Hello, sir.
Hi, Amy. How are you doing?
I'm very well, thank you. How are you?
Good, good. So, Amy, we are going to start a new unit today. Basically, we'll start with Pascal's triangle, which is a fascinating thing. And it finds huge importance in mathematics and makes especially counting and working with numbers very simple when it comes to sequences and series. One full branch of mathematics, which is combinatorics, in which we always discuss about Pascal's triangle and many other things which have come from there. So I'm very excited to share that with you. Let's see how it goes. Are you ready?
Okay. I'm looking forward to it.
That's great. So we'll begin with that. Screen, can you see it now?
Yeah.
Pascal's triangle. Okay. So Pascal's triangle is very interesting, Amy, and it finds hundreds of applications in mathematics. And if you are doing something with numbers and counting numbers or adding series or sequences, you'll always come across this. Something which is so simple to understand and sometimes very difficult to, comprehend. This something like this. And it is simply called Pascal's triangle because it is just in the name of the mathematician, right? Blaise Pascal, who discovered this particular pattern. We'll now discuss how we can use it in so many different ways, correct? So the triangle which you see on the right-hand side starts with 1. And then when you go diagonally down in the triangle, you see only the number 1s. Do you see that?
Yeah.
All these numbers are 1, both these sides. Both these sides, the numbers which you see are just 1s. And the numbers in between, you get them by adding the above 2 numbers which are closest to that. So for example, the top 2 1s can be added to get 2. And so in that particular cell, you can fill in 2, right? And you see that little triangle. So triangle grows as you go down, and you can fill in the numbers just by adding the previous 2. So I've highlighted these blue color 4, 6, they add to 10. Similarly, 6 and 1 adds to 7, 7 and 21 adds to 28. So likewise, you can fill all these numbers in this particular triangle. So the triangle is bordered by 1s, and the numbers in between are sum of 2 numbers closest immediately above, right? So the entries in the triangle can easily be generated, right? For example, I have got the last entry where I have the numbers 1, 8, 28, 56, 70, 56, and so on. As an exercise, what you can do is add the next row into this particular triangle. So for example, if I want to add the next row, what number should come here? Can you tell me between 8 and 28?
36.
Correct. You'll just add them and you get your number. Likewise, you can add all the numbers, right? Now, we will see how to specify each and every cell in a particular triangle, which is our Pascal's triangle. Of course, you can say them rows. The other thing which we look into is we call them as diagonals. And now let's look into that part and also see how we can actually tell which number or cell we are talking about. Correct? So as you can now see in this particular screen that we have these different rows. However, the very first row which you see in the Pascal's triangle has been numbered as row 0. So it's very small, you can see row 0. So the first row actually is called row 0 for Pascal's triangle. Then every row is 1, 2, 3, 4 as you move downwards, right? The other thing is along the diagonals, and the diagonals are also numbered from 0, 1, 2, 3, and so on. That's very critical to understand, right? So the very first term which you get here, right, is at the crossing point of the row, which is 0, and the diagonal, which is also numbered as 0. And so we'll call this as our term T00. Correct?
Oh, okay.
Right. Now the second number, let's look into this now, which will be in row number 1, because next row is row number 1. And still you're moving in the same diagonal. So it is T10. Correct? The next number which we get into will be in the same row, which is row number 1, but it is the next diagonal, which is 1. Now, referring that cell with the diagonal becomes slightly more complicated. Because, if it is a big triangle, for example, if I'm looking at some number here, correct? Then which diagonal it is, I mean, I will have to count from that side, correct? You have to count one way or the other, but anyway. So in that case, what we figured out that it is easier to count from this side. We can say 0, 1, 2, 3, 4, 5. And so this cell, I could say, this is actually the 7th row number, right? But as far as the diagonal is concerned, this diagonal is number 5. But I can get to this number 5 by counting from the left side, right? Like you normally count, right? Starting with 0, of course, is Pascal's triangle. 0, 1, 2, 3, 4, and 5. Do you see that? So, so it becomes 5th position now. So we will refer to our nomenclature. We'll say it is TNR, right? TNR, where actually speaking, N is actually the row number. R is not the row number. R is the position number. You can also say diagonal. But practically we are always counting the cell from left to right. We are not counting the diagonals, and therefore we just call it a position. Is that clear to you? Counting from left, right? So many times we may use position, but not diagonal, right? But to be very clear about it, a cell is defined by row and the diagonal in Pascal's triangle, where both start with 0. This is very important to understand. Correct?
Okay. Yeah.
So each item in Pascal's triangle is defined by row n and diagonal number k. So I have not used R for it. I'm using k, another alphabet. Intersection of row and the diagonal is the position R. So this R is the TNR number, which is the position from the left side, counting with 0. Okay. If TNR represents the term in a row n, position R, then TNR is Tn minus 1 R minus 1 plus Tn minus 1 R. So that means previous. So n is the nth row, n minus R, n minus 1 is the row before it, n minus R, right? Similarly, R is that particular diagonal or the position, and R minus 1 will be its position above and left, and exactly above will be R, correct? So we have two terms here. So the previous to this, for example, will be, if I have T7, 5, then the numbers previous to this will be T6, 5, and T6, 4. Correct. Those will add to give you T7, 5. Is that point clear to you?
Yeah.
Key. We call this as an iterative formula to generate all the values within Pascal's triangle. Correct?
Oh, okay.
So because it can be repeated over and over. Perfect. Now here's a question for you. Example number 1, based on what just we learned, right? Use Pascal's method to write formula for each of the following terms. T10R. How can you write T10R as a combination of other two terms in the Pascal's triangle? Tell me.
So the one before would be T9.
Yes.
To T9-2 add T9-3.
Perfect. Perfect. That is how you have to do it. Similarly, if it is T99-80, one before is 98. So you can write both the terms with T98, correct? It is before. And then as far as the diagonal or position is concerned, 80 for the next one, and one before would be 79, and very simple to get it. Perfect. So that is how you have to get your numbers. The next one, I have just given a general formula, Tn plus 1 and R plus 1. So now you can write the formula for that also. Clear?
Yeah.
Now let's do example number 2. So Amy, can you read this example and answer for me?
So example 2, Pascal's method. Use Pascal's method to write the value of the following terms. A, T8, 5. So we go to row 8.
So you can recognize very easily where in the first diagonal, these are the numbers, actual numbers of the row defined by the Pascal itself, right? So clearly in this position will be 0. So that is your 0th row. Do you see that?
That makes sense.
So
yeah.
when you see this 8, we are talking about T8. And now 5 you will count, which is the position, and tell me what is the number written there.
Wait, so
0, 1, 2, 3, 4,
17.
and this will be 5.
Oh,
so
yeah.
you have to start with 0, right? So we say 0, 1, 2, 3, 4, 5, correct? So this number will be 56, clear? So once you make your triangle, easily you can identify the number. Now, how will you find T95?
T95, so, so there's no T95, so we would have to do the two,
Yeah,
so
we
the two
add them
before,
up.
and then add them.
Add them up to get T95, 70 plus 56, you will get 126 as your answer, correct? So that is how you're going to get. And T105, you have to make T95 further down and then do it. So that is an exercise question for you. So I will share the video with you. Then you can go through this exercise and answer it. But this concept is clear to you, right?
Yeah.
Okay. Now, another way to look into these is example number 3. We are calling this as Pascal's method, basically application of your iterative formula. So can you please read and answer this question?
So express as a single term from Pascal's triangle. A, T12, 5. Is that how you read it?
Yes.
T12, 5. Okay. Add T12, 6.
Yes.
So that would be T13, 6.
Perfect. The next one is, do the next one.
Okay. T53, 29 minus T52, 28.
Correct.
There's a minus.
Yes. So we rearranged it. Do you understand?
Oh, you rearranged the, the formula. Okay.
Yes.
So that means the answer we're looking for would be, so since the other term is 1 less than the 53, and the other term is 1 less, so we're looking for T n minus 1 r.
Yeah.
So so T52, 29.
Perfect. 29. That is correct. Got the idea. The next one is the general formula. When you rearrange, and how do you write the formula? So now can you complete this formula? Tnr minus Tn minus 1 r will be equal to what?
Tn minus 1 r minus 1.
Perfect. So that is how you work with this. So this is very important, and that's why we went through these 3 examples to understand the nomenclature. Now here is a test question based on our learning. So in test, normally you will be given something from in between the triangle. So here is your exam question 1 on Pascal's method. Fill in the missing numbers of this part of the Pascal's triangle. So we are given 36, 84, 126, and 210. The green are the cells which you need to fill in. Can you tell me how will you get this number here?
By adding 36 and 84.
Perfect. And this number?
By so 210.
Subtracting from here to this, and that is why how you're going to move, and you can fill in this particular case. So try to do it once I share the video with you. Correct.
Okay.
Now that was just to give you starting on numbers, how to work with these numbers. We have to do a lot of those things. Now here is example 4. Explore patterns in the Pascal's triangle, right? So again, the same triangle is shared with you with the rows numbers and diagonal numbers. There are so many patterns which you can find. So what I did was that I just wrote, you could find sum of a row. So this is a particular row. For example, you can add them all and see what you get. And then if you do for a couple of rows, you will see a pattern. So you need to recognize those patterns and come up with something, right? Similarly, do you see any symmetry in this particular case?
Yeah.
What kind of symmetry do you see?
So when you I don't know how to describe it, but when you look down the middle, it's like a reflective.
Yes. So the terms from the left side and from the right side, they're exactly same. Correct? So that is the kind of symmetry, right? So of course we have a symmetry, right? So it is. So if there is a odd numbers like in the particular row, in that case you'll have one in the center and exactly same thing. But if it is even numbers in the particular row, they'll be duplicate same numbers right in the between. For example, we have 35, 35, correct?
Oh, right, okay.
Which is the seventh row because we started with 0. Now, so remember that we started with 0. So the row number and the even number of row is kind of different concept. Here, the first row, which you will think is row 0, 0 is not even. Here, the first row is odd number of row, right?
Just a quick thing.
Yes.
Whenever you talk about rows, are you saying it in Pascal's triangle, that row? Or are you saying, oh.
Yes, very good question. So whenever we are using the Pascal's T and R formula, right? In that case, the row number starts with 0, 1, 2, 3, 4, right? Okay. Now, if we are referring Pascal's triangle from somewhere else, right? For example, we will be referring this from binomial coefficients. You'll soon see, right? So it is outside Pascal's triangle. When we refer from outside a triangle, when we say the third row of the triangle, when I say third row of the triangle, that means this is my first row, second row, third row. Actually, it becomes the second, n is 2 for that.
Oh.
N is 2 for that, as far as Pascal's calculation will go, right? So for example, this particular row, right? So this particular row is, as far as Pascal is concerned, Pascal's triangle is called row number n equals to 3. Correct?
Right. Yeah.
But if I have to refer it from outside, I will say the fourth row. 1, 2, 3, 4. The fourth row in Pascal's triangle. What does that add to? What is the sum of elements in the fourth row of Pascal's triangle? So, you know, I'm not an expert now on Pascal's triangle. The topic is not Pascal's triangle. The topic is binomial theorem, right? So, and you're just given a triangle. So when you look at that triangle, you'll start counting by 1, 2, 3, 4.
Yeah.
Not with 0.
Oh, okay.
So it's
a tad bit confusing.
It is very confusing. You have to make a judgment, right?
Yeah.
Okay. So this is my triangle. 1, 2, 3, 4. Okay. So it is. But when you refer to Pascal's triangle, the number kind of switches. So it is a very simple thing where, as we move along, I think you'll get the hang of it, right?
All right.
Yes.
So all you're saying is, if it's from an outside kind of source, you always count row number
1, 2,
from
3,
1.
4.
Yeah. But if it's saying it's Pascal's triangle and using
number,
T
yeah,
and
then
R.
it is 0, 1, 2, 3, 4.
Okay, got it.
Yes.
Yep.
So, and if I write T and R, it clearly means 0, 1, 2, 3.
0, 1, 2, 3. Yeah. Got it.
Right. So it is a very interesting triangle and it has a lot of patterns. All these patterns you can actually observe. Sum of a row is 2 to the power of n. You will see symmetry, as you just pointed out. The terms from the left side and right side, they're exactly same. Same distance away, they are same value. Triangular numbers. If I place all the numbers in forming a triangle, like if I put pennies, right, for example, and make a triangle, you can count the numbers. And the row, which gives you the exact count for triangle numbers, is the diagonal, this diagonal, right? Now again, very important diagonal. As far as Pascal is concerned, Pascal's triangle is concerned, it is diagonal number 2, right? Yeah. But when you read a statement, it says diagonal 3 represents the triangular numbers. Do you understand my point? So when we refer as a statement, we say diagonal 3 represents the triangular numbers. Diagonal 4, which is actually diagonal 3 of Pascal's triangle, represents the quatic number, tetrahedral numbers. So if you have a tetrahedral shape, for example, if you put 4 oranges and then make a pile of those oranges, correct? So, right? So in that case, you can count by using Pascal's triangle. It has that number in it in a sequence. So if you just put 1, it'd be 1. Then if you put more than that, then there's these numbers in between will give you exactly how many are there. Is that clear to you?
Yeah.
Everything. So those are the diagonal numbers. Now, diagonal sum will explore this property that diagonals also add up to something. Just to be very critical, you know how to add natural numbers, correct? So let me give you an idea here. if I have this, these are natural numbers, right? Diagonal 1, which is the second diagonal, diagonal 1, which is the second diagonal, has got all the natural numbers, 1, 2, 3, 4, 5, 6, correct?
By natural numbers, you mean?
1, 2, 3, 4, 5, 6, starting with 1.
Oh, is that it? Just
natural numbers. Yeah, whole numbers start with 0, correct?
Yeah.
When I say natural numbers, 1, 2, 3, 4, counting. The numbers which we count, counting numbers. So, you know the numbers, if I have to add 1 to 100 numbers, what do? N times n plus 1 divided by 2. We have a formula, right? We just calculate. So, sum of 6 numbers will be 6 times 7, which is 42, and half of that is 21. You see that 21 written here?
Oh, yeah.
So, first 6 numbers, sum is written there. So, it's kind of moving in the diagonal, and then you move down to see the sum. Do you see that? So you can.
Is that anywhere on that line?
Anywhere,
so if you stop at 4 and go down 10, is all of those add up to 10?
Add up to
7,
10.
8, 9. Oh.
Yeah.
10.
So it's a beautiful sequence. And you'll see the sum lies on the second diagonal, right? Do you see that?
Right.
So you can have a formula. So that could be a question, for example, generate a formula for finding the sum of numbers using Pascal's triangle. So you can add them all and get the cell where the number lies. Okay. Oh. You will also notice that we could actually find perfect squares from this particular triangle. For example, to give you a heads up, 10 plus 6 is?
16. Oh, perfect.
10 plus 3 is?
4.
10 plus 15 is? 25. And so if you add along the diagonal 2 of Pascal's triangle, which will be referred to you as diagonal 3, third diagonal, triangular numbers, that series has adding any two of them give you perfect square, right? And you can also find the sum of squares using these diagonals and the numbers in the pattern which we are going to explore. Okay, so that is to say, if I have to add the sum of squares of these elements, let us say, which is 1 plus 3 square plus 3 square plus 1 square, which is 9 plus 1 is 10 and 10 is 20. You see a number 20 here, right?
Yes.
So the number is, you were looking at the row which is this, and twice the row right in the center is your total. So you have a formula with which you can actually add the squares of the numbers and read it from the Pascal's triangle itself. So do you see, just to begin with, how much information is there in this triangle to explore?
Is that all of the patterns, or is there more?
There are many more. Many. This is just to introduce you to some very popular ones, okay? You will when we move along, many patterns could be do, and people are still discovering many, okay? So there's no end to it.
Oh, yes. That's so cool.
Okay, so this brings us to another beautiful pattern. We were just talking about that. Okay, number of paths. Amy, I'd like you to read this, whatever has been written here.
All right. So explore the number of shortest grid path from a given node to the top. Move diagonally up for the shortest grid path. Yeah.
What I'm trying to say here is, give a node to the top. So let's say we are given this node where the number 4 is written to us. And from 4, we have to move up to the top level, right? Let's say as if you're climbing a mountain, how many different paths could be there to climb that particular mountain? That is the question, correct? So that kind of question can be solved so easily here. As you can see here, I've highlighted all the possible paths from 4 to the top, right? So you could go straight in a diagonal, then 1, or you could turn 1 before the end, right? Or you can turn 2 before that and turn, or you just first turn and then go right. Perfect. Yeah. These are only the 4 ways you can go up. That's what we mean. Move diagonally up for the shortest grid path. They all have 1, 2, 3, 4 steps. And the number 4 gives you the 4 answers. 1, 2, 3, 4 are the possible paths. Do you see the beauty?
Oh.
These are the only.
Wait, so you're saying, because it's the number 4, there are 4 paths?
Yeah.
So if it's number 6, there will be 6 paths?
Yes. If you're at 6 and you try to make these paths, there will be 6 paths. And of course, if you start from here, you have already taken 4 from one side, 6 from the other side. So there are 10 paths in all.
Oh my God. That's so cool. What? Oh my god. That's so easy to remember. Like if anyone said, how do you find out the number of parts? You don't have to sit there trying them all out.
Just make a Pascal's triangle. And there you go. And we'll actually show you how beautifully we work with number of paths, because, you know, this is like architecture. You make a city and then you build so many different paths, bridges, and this bridges, construction going on, that road closed, this road closed. You can actually figure out how many ways to go from one place to other using this concept.
Oh my God. So all the, like the way the city's built, ages, like years and years ago, it's based on...
You can count, yes. You go to a monument, you want to figure out how many paths to go up. This is the way, correct. Some portions may be blocked or broken. Even then you can solve the question. Even then you can solve, I'll show you how, okay, in this particular. Right. It's going to be very interesting. So can you read further, please, for me?
Yeah, so entry in the Pascal's triangle provides the number of shortest paths to the top.
Correct.
So, yeah, so in this example, 4 paths are there as shown from the node with entry of 4 to the top.
Perfect. Now it works both ways. If I want to come from top to a position, let's say, if I want to travel from here to this position, there are 5 ways to do it, okay? From going from this to this. That means now we'll be moving down, or right, or diagonal, right? Down diagonally, right? Do you see that? So that is how you can reach a particular spot. So it could work either way. Perfect. So that brings us to some very beautiful exercise. So here we have paths to London, and we'll figure out how many ways to reach London.
Right.
So what I've done here is there are 4 different figures. So these are not those 4 paths. These are totally 4 different questions for you. Practice questions for you, right? We'll do one of them now. So we'll see if let us say this is my city of London here, and there are 2 gateways to reach at this particular point, right? And we want to start from this particular end. Then how many paths are there to reach London, right? So there are 2 different positions you could reach there by bridge A and bridge B, and these are the different ways, right?
Right.
Can you please read the question?
Yes. So in the arrangement of letters, start from the top and then proceed to the next row by moving diagonally left or right. How many different paths will spell each word?
Correct. So our first word I've taken is London. So can you help me find how many different ways can you reach here at N to so that your word London can be spelled completely? Yes, tell me. How will you do it?
Okay. So already 1 path is given, which is all in green.
Okay. So we'll do Pascal's
and then
we'll just write numbers. Because, you know, if you get the number, you know the answer.
Okay, so write all ones on the...
1 on the diagonals, right?
1 on the borders, yeah.
Easy.
And then on the other borders. Then 2, 3, 4, 6, 4, 5, 10, 10.
10 and 10.
Oh,
so
the
10
X
and 10 is 20.
20.
Answer.
Oh. What? I was expecting it to be longer than that. Oh, okay. Yeah. I get the gist now.
Got it?
Yeah.
Now remember, when you come to this particular type of a pattern, we have blocked few paths. You cannot go further, right? For example, here, you may say 1, 1, 1. That is fine, correct? You will write 2 here, that is fine. You can add 1 and 2, get to 3, and here also you get to 3. But now, moving to the next position, there is only 1 way, right? Because you cannot add the other number. Blocked means 0. So 3 plus 0 will again give you the number 3 only. Is that clear to you?
Makes sense, yeah.
On this side also, it has been blocked, so that will give you 3 only. So reaching H at these 2 points will be 3 here, 3 there, correct? And here also it is 3, and here also it is 3. So the total paths will be 3 times 4, which is 12. Do you see that?
Why is it 4? What's all the letters at the bottom again? Are they all H?
Ganesh. This word was Ganesh.
Oh, okay. So are they all H at the bottom?
H, yeah, all were H.
Oh, okay.
So you can spell so many different ways, right? Following these paths. So each number at the end will be added because those are the total number of combinations, correct?
Yeah, got it.
You get 12 as your answer. So if there is a block, even then you can work it out. So this is another question for you to practice and enjoy, right? So this is like fun part of it. Enjoyed it?
Wait, yeah, I did.
Yes.
Was this the thing you're talking about the blocks with the whole city?
Yes.
Oh,
so
okay, makes sense.
Treat the block as 0, correct?
Yeah.
Because you can't go there. So that is not adding to your paths. You are going straight, keep on going straight. I mean, come on.
Yeah, I can't believe it still works though with blocks.
It works. Yeah, so any kind of hindrance cannot stop this. Perfect. So that was the part to introduce you with Pascal's triangle, and moving on with applications. The huge application of Pascal's triangle is binomial expansion. So that is the major part, and that is the next chapter for you, Amy. Okay. Binomial expansion and Pascal's triangle, correct? You know all this. So let's summarize. Anything to the power of 0, you know, is 1, correct? But if I put power as 1, a plus b to the power of 1 will be a plus b. And what is a plus b whole square? A square plus 2ab plus b square. Perfect. Right. And a plus b whole cube is, if you don't know, go to the Pascal's triangle. This third row. The third row of Pascal's triangle gives you the coefficients 1, 3, 3, and 1. So you can now place 1, 3, 3, and 1 and get your a plus b whole cube. You get the idea.
Oh my God. Yeah. So that would work with like a plus b to the n. It would work with n.
Yeah, we don't know what the a plus b to the power of 4 is, correct? But we know the Pascal's triangle numbers 1, 4, 6, 4, and 1. So now if I have to expand a plus b to the power of 4, I know a few other things about the binomial expansion, that the power sum is always same, right? It starts with the maximum power of the first one, and that reduces by 1 each time. The other one increases by 1. The sum is same. Exponent index is same. So a plus b to the power of 4, what we can do is we can write a to the power of 4 to begin with, a cube 3, a square, b square, ab cube, and b square. But we don't know what the coefficients are. Pick them up from Pascal's triangle. 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. You're done.
Oh, okay, yeah. And then the sum of the exponents would be equals to n.
2 to the power of n, if you add them.
All right.
Yeah, some of the exponents will be n. Sorry. What you're saying is a different thing. Yes, a and b exponents will be 4 all the time. So that you know from the Pascal's binomial theorem expansions. So if you have to the power of n, you have always n plus 1 terms, right?
Right.
So for to the power of 4, we have 1, 2, 3, 4, 5 terms. Every term has a coefficient which will be taken from the Pascal's triangle, 1, 4, 6, 4, 1. And the variables will be adding their exponents to 4 each time, right? In particular order, correct? Do you see that part?
Yeah, so cool though. Like, how did he even come up with this? It has so many functions, like, and so easy to do. Like, if you had to expand that, not in a million years, I would be sitting there doing every single one. If it said something to the end, like, let's say 7, but it's so easy just to read off the thing and get it.
Correct. So if I say expand a plus b to the power of 7, right? Now we are in the context of binomial theorem, correct? So we'll say the row will be 7 plus 1, 8th row. Do you understand? But which is actually number 7 for Pascal's triangle. But when we refer it from the binomial side, we will say 8th row, because we are counting like this: 1, 2, 3, 4, 5, 6, 7, 8. You get my idea?
Yeah.
8th row. But to be very clear about it, this number here identifies with your n, 7. So when you are interested in a plus b to the power of 7, the number 7 should be definitely there, right?
Okay.
Which is the second number, right? In Pascal's triangle, we'll refer to this as T1, right?
Yeah.
7, 1. But here we are saying it is the 8th row in the Pascal's triangle, which will give you all the coefficients for a plus b to the power of 7. You get my idea? Very critical. So,
or could you think, or could you think of it like, if it says it to the 7, just find 7 on Pascal's triangle?
Perfect. And do your job. Yes. But the problem here is in multiple choice question. In the multiple choice question, the statement is which row in Pascal's triangle corresponds to a plus b to the power of 7 for the coefficients? Now what will you answer? You have to answer 8. You get an idea. So that makes huge difference because they're not really seeing the result. You know the result, I understand that part. But picking up the right number, multiple choice question is so critical. That makes this point very, very critical. You have to see in which context the question has come and from where it is coming. And then accordingly, you have to put the number 7 or 8, right? So you have to be very cautious about it. Perfect?
Yeah.
So straight question is here. Can you please read question number 1 here, right?
So state the row of the Pascal's triangle that would give the coefficients of expansion 2x minus 3 to the power of 24.
Yes.
So the row of Pascal's triangle. So it would be, because we're doing the 1, 2, 3, 4 thing, it would be 25.
Correct. That's the answer. 25 is your answer. I know you will pick up the row which is Pascal's 24th.
Yeah.
Starting with 0, but not when we are referring it from outside. So let this point be very clear because these days, multiple choice questions, right?
It's because the question saying row of the Pascal, like it's saying of the triangle. So you're saying refer to the triangle, but then you're saying it from the outside. That's what's confusing. Because if it's of the triangle. Yeah.
I've tried to figure this out many times. Sometimes I use the word of in the Pascal's triangle or of the Pascal's triangle. I know it makes huge difference, but the way questions are worded, you have to see the perspective.
Okay.
From where the question is coming and then answer the question, okay?
All right. Okay.
So from binomial theorem side, they don't know that Pascal is starting with 0, okay?
Yeah.
That's the whole thing, right?
Right. Got my head around it.
Correct. So now we have these binomial coefficients, and what I have done here, these numbers which you see in the triangular form have been now placed in rows and columns just for ease. Do you see that? So they are the direct coefficients which you can place and then get your expansion for any binomial expansion. Do you get this idea, right?
Yeah.
Now, many times I know binomial expansion and binomial coefficients is your next chapter after this. But since we are overlapping the two things, I will introduce you to some more concepts which you'll learn in next chapter. No, because we can go hand in hand rather than coming back to Pascal's triangle and then going, right? As you can see how closely they are related, right? So that's the whole idea of my taking up something from your binomial coefficients and now breaking from Pascal's triangle and getting to binomial coefficients, correct?
All right.
So let's talk about binomial coefficients just when we are here. Binomial coefficients in the factorial form, right? So factorial form, if you, let me revise that also. So when I write 7 factorial, it means what? It means 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1. So it is product of the natural numbers up to 7, including them all, right? So that is factorial notation. So these notations are used to shortcut, you know, sometimes when we're talking about series, there are too many numbers to write. So you can precisely write them, correct? This is one term which is used. Now in binomial, what we say is each coefficient which we talked about is also referred to as NCR, also written as CNR, CN comma R, and also written as this particular bracket, writing N to R. Is it okay? So in this particular case, when it is used, we say you have to choose R, right? N choose R, N choose R. Now that comes from your next to next chapter where we are looking into permutation and combination. Is it okay?
Oh, okay.
So
how come there are 3 forms?
Oh, this is so useful, right? Permutation combination, correct? So then the whole unit will be winding before probability. So we are going to learn in this particular unit Pascal's triangle, binomial theorem and its coefficients, and how to use them, permutation and combination, and this forms a part of our counting principles, right? So combinatorics.
Are the different?
Yes.
Sorry, are there different forms for different situations, or can you choose?
About which you're talking about this?
Just the NC, yeah, because they all mean the same thing, right?
Okay, so I'm teaching students globally. So when it comes to different countries, they follow different standards, right? Even in the same country, you have different standards. So they write in different way. So many books, you'll see NCR, you may see that different ways of writing it, but it means N choose R. Now, let me tell you about N choose R also. Let us say on your shelf, we have 10 books, right? And you have to select 3 of them. In how many ways can you select 3 books from those 10 books? The answer is NCR. So 10 CR, 10 choose 3. So that number you can read from Pascal's triangle also. And that number is so useful. We have a formula to calculate also, correct? So
do you use the calculator for that?
Yeah, and calculator has a function, NCR.
Oh, okay.
And this is the formula which is also mentioned here, so that when the numbers are very big, we cannot make a triangle that big, correct?
Right.
Up to 10, the triangle is good enough. But after that, we use the formula or your calculator to find the numbers, right? So we are going to use the formula, which is NCR. I will say NCR. Normally it is said N choose R, right? If you write like this, in this fashion, it is N choose R. That is how we say. NCR is when we write like this. Is that?
What about that one? How do you say that one?
CNR.
In the middle.
CNR.
CNR. Okay, cool.
So different ways in different regions, they just say the same thing, right? It means one of these things, okay?
Okay.
So N choose R means N factorial divided by N minus R factorial times R factorial in the denominator, right? So that's the formula. So when we use this particular formula and N choose R for probability, we use this particular symbol, N choose R. It means N choose R. And in binomial theorem, it is convenient to write NCR, right? Because it's convenient to write NCR rather than making brackets and writing like that. So in the books, when they use binomial theorem, they normally use NCR.
Okay.
But you know, I don't know what exactly will be there in your books, but you'll find different nomenclatures. But these are all common. Okay.
Got it. Yeah.
Now let's get back to our where were we? N equals to 8. Okay, this table gives you N equals to 8. You remember we had the numbers 1, 8, 28, 56, 70, and then there's a symmetrical thing, right?
Correct.
Pascal's triangle. So I've copied this Pascal's triangle. I just cut it off and put the portion here. The 8th row of Pascal's triangle is actually the 9th row. So that means this one. These are the numbers, and because they are symmetrical, I just squeeze the other thing to save the space, correct? Now the idea here is, how do we calculate these numbers? You saw that there is one-to-one correspondence between the Pascal entries and the binomial coefficients, right? So when we are writing T and R, we could also write C and R. Or NCR, right? So T and R can be replaced by C and R, right? They're exactly the same numbers. Now, how do we calculate? That is the beauty of your binomial coefficient C and R formula. And that is, number 1 is always 1, you know that, right? So you begin with 1. The next number in the 8th row will be 8 times 1 times 8 over 1, and then times 7 over 2. Then the next number is times 6 over 3, and the next number is times 5 over 4. Then you reach the peak when you reach the center. If there are odd number of numbers, there will be one number in the center which will be maximum, right? And then reflected on the other side, you copy them out. But if there are even number of numbers, right? In that particular case, as this is an odd number of numbers, it may say 8, right? But it is, you know, the 9th row, correct?
Yeah.
Odd number of row, right? So we have odd numbers here, even in Pascal's binomial coefficient. When you have the index as 8, there are 9 terms. 9 terms means odd number of terms. So you have a maximum and then it'll taper off, right? So you have a maximum value of 70, and you can now write those 56, 28, 8, and 1 to get the rest of the numbers on the right-hand side. But see how easy it is to calculate your numbers. So first probably 1, and since we are talking about 8, 8 over 1, 7 over 2, 6 over 3, 5 over 4 gives you combination of all the numbers. You see that?
Wait, but what's the question?
The question is to find these numbers, 1, 8, 28. How do we find these numbers? The question is like this. Let us say you want to find the numbers in the ninth row of Pascal's triangle where n equals to 9. Tell me what are the numbers without adding those ones. One way, of course, is you will say 1, and then you will say this is 9, and then you will add this up, right? You say 36. Correct? You could do that. The other way is the numbers are 1. The numbers are 1, and then you have times 9 over 1. This is the second number. Then you have 1 times 9 over 1 times 8 over 2. Then the number is 1 times 9 over 1 times 8 over 2 times 7 over 3. So you get the third number. Do you understand?
Oh, okay, yeah. So that's another way of getting the coefficients in a row.
Yes, easy mathematical way, and it really works very well since, you know, the numbers could be very big. If I say, what is 50C5? Now, you're not going to make a triangle like that.
No.
You can calculate like this, correct? 50C5, you have to do only 5 products to get to that number. Or use the formula, which is right there for you, correct? Understanding the meaning, 50C5, just the formula. Is that clear to you? So you can get every cell number.
So with 50C5,
yes,
because of the 5, do you start with 5 times 50 like that? Or do you always start with 1?
Okay, so 50C5 you could do like this. 50 times 49 times 48 times 47 times 5 numbers write down. 1, 2, 3, 46. Divided by 1 times, 2 times, 3 times, 4 times 5. Done. That is 50C5.
Oh, okay. Yeah, got it.
You got the idea, right?
Yeah.
So easy now. So I've shown this method right here. Let's explore this 8 series. So 8C3, we are looking at this particular point. 8C3, correct?
Yeah.
So 8C3 is 8 times 7 times 6 divided by 1, 2, 3. So there are 3 numbers which are getting multiplied in the numerator and also in denominator, increasing and decreasing order. So 8C3 is 876 over 1, 2, 3. Got it? So you have this number, it comes when you calculate 56, easy calculation. Correct?
Also the other stuff.
Yeah.
It says 8765, like that.
Yeah. So what I've done here is to 876, we just added product 5, 4, 3, 2, 1, both in numerator and denominator, right? Still, the product is same, which is 876 over 1, 2, 3, correct?
Oh, because they cancel out.
They cancel out. But I can use factorial notation. The idea here is to use factorial notation. So the top one is 8 factorial now. 8, 7, 6, 5, 4, 3, 2, 1 is 8 factorial. And in the bottom, we have got 2 factorials. One is 3 factorial, correct?
Yeah, because it's 3, 2, 1.
And the other one is 5 factorial. So we broke them out and we wrote them as 3 factorial times 5 factorial. You get the idea. And now see the formula. 8C3, so n is 8. So the numerator is 8, n minus r, which is 8 minus 3 is 5. And the number 3 itself. So you have a correlation between the two.
T and R.
Do you see how it works? That is how the formula works.
That makes sense. Yeah.
Extremely important. I mean, I'm telling you, it takes a lot of time to understand the whole picture of it. But once you do it, you can sail through the whole unit 1, just with this concept.
Wow.
You understand n choose R means to select n items from the R, right? Choose. And you also know now how to calculate the value. We have learned 2 different ways of calculating the values. One is just by multiplying like this. The other one is using the factorial notation. And of course, you can use a calculator if the numbers are very high. Does make sense?
Yeah, but just one more thing.
Yeah.
So there are 2 ways of doing it.
Yes.
So I get so when you say n choose R.
Yes.
The n is, well, let's say a total, and then we're choosing, let's say 2, if it was 2, we're choosing. You take 2 of the total and you divide it by 2 numbers at the bottom.
So let's do one thing. Well, let's take a number 6, C, let's say 2. Small number, correct?
Yeah.
That basically means 6 factorial over, what is 6 minus 2? 4. 4 factorial times 2 factorial. This is one way of doing it.
Yeah.
Other way of doing this is 6C2. So I will multiply, let me use a different thing. I'll multiply 6 with 7, 2 numbers, and divide by 1 times 2. So I get the answer.
6 times 7? Why can't it be 6 times like 5?
Oh, I'm sorry. You're right.
Oh.
It has to be 6 times 5.
Okay, so yeah. And then 1 times 2.
And so 30 half is 15. Do you see that?
Mm-hmm. Yeah.
We get our answer. 6C2 is this much. And even otherwise, when you do, you'll get 15. And if you go back to your triangle with the numbers, 15, 6 is this, and this is 1, and this is 2. 15.
15. Mm-hmm.
0, 1, 2, and that is the 6th row, correct?
Right. Yeah.
Pascal's triangle, 15. Mm-hmm. So you get the same calculation either way, correct? And perfect answer with this calculation.
Could you just re-explain the 1 times 9 times over 1 method again?
Sure. Let me erase this, and then we'll do it, right?
With the same.
Yes.
Constant. Yeah. Cool. Thanks.
So what we're trying to figure out here is what is 9C. Let's take a smaller number, 9C3. Okay. Right? That basically means you are actually starting with 1. So I'm not writing 1. So I'm writing 9 over 1 times 8 over 2 times 7 over 3. That is my answer, correct? So you can always calculate this. Easy calculation. So you can deduct whatever, simplify, correct? You see that? 3. So you get 12 times 7 as your answer, right? 12 times 7 as your answer, which is 7 times 2 is 14, 84. Is that clear to you?
Yeah.
One way of doing it. The other way is 9 factorial over 9 minus 3 factorial times 3 factorial.
3 factorial.
Which is 9 factorial over 9 minus 3 is 6, 6 factorial, 3 factorial, correct? The last way to do it is go to the Pascal's triangle, 9C3. So that is your next row. So you have 1, 2, 0, 1, 2, and 3. So that is your position, correct? So you can add 56 and 28 and get your answer.
Got it, yeah.
And it is 84. So you can read from your Pascal's triangle the same number, use calculator, and choose R.
Get the same many. Yeah.
So you should know all the ways, because one of the tests could be without calculator. When it is without calculator, these calculations which I am doing right here help. This is the fastest way of calculating. Fastest way of calculating and choose R. Is that clear?
What's the name of that method?
No names. Pascal's method.
I need a method. I want like names. Like I would call the factorial one like calculator.
Okay. And then, this is just the formula, right? This is just the formula.
Yeah, just formula.
This is well,
non-calculator.
We might come to a name. I'll share with you that next time. Okay.
Okay. I like names.
Move forward. I think you're finding it interesting. Let's move forward. And see, now what I've done here is just to summarize few terms which we have just used, right? Okay. So we'll talk about the sigma notation. Sigma is kind of sum. As you've seen, we are adding all the numbers, right? So the binomial theorem itself is a series which is added, right? All the terms are being added, for example. So sometimes we just want to represent it like a polynomial, you understand? an x to the power of n plus an minus 1 x to the power of n minus 1, the whole series.
Yeah.
We represent using sigma notation. So in this case, a plus b to the power of n can be written as NCR. Now you understand that's the coefficient times a to the power of n minus r times b to the power of r, right? So n minus r and r, when you add, you get n. And you have increasing and decreasing powers. It works with the definition, correct? And you know, R is somewhere between 0 to n, including both of them. So you have a whole series with you, correct? And this is your binomial coefficient. We have also seen it has a formula which helps you to calculate things very easily. And n factorial really means n times n minus 1 times n minus 2, so on till 1. All set of natural numbers multiplied together, correct? So here we have summarized with whatever we have learned about so many new terms which will come in this chapter. So, Amy, can you read from here what we have written?
Yeah. So sigma notation for writing binomial expansion of a plus b to the power of n is a plus b to the power of n equals that sigma notation thing. Then n choose r, a to the power of n minus r times b to the r, where r is in between 0 and n, both being included. And n choose r is the binomial coefficient.
Perfect.
Continue. Yeah. So n choose k, read as n cr or n.
Yeah, it should be r. Yeah.
Oh yeah. It really signifies the number of choices to select r elements from a group of n elements. So yeah, so it can be calculated as follows. So that's the formula. N choose r equals n factorial over n minus r factorial times r factorial, where, like you said, n factorial is
product of natural numbers of 2n.
Naturals.
Yes.
Pascal's triangle provides direct values for n choose r as n choose r equals tnr.
Correct.
tnr is the r element in the nth row of Pascal's triangle.
Yes.
Since rows in Pascal's triangle are counted from 0, the nth row is actually n plus 1 row in the triangle.
In the triangle. It's slightly confusing, but that summarizes all what we learned about Pascal's triangle as far as the numbers and reference is concerned, correct?
Yeah.
We have already seen so many applications of this particular triangle. Now let's move forward and apply some of them now. So we have this question which says patterns in binomial expansion. So as I said, the next chapter is binomial expansion, and there's so much of common things between the two that I thought I'll club some part of it now, and that will help. And then when you do the next chapter, I'll pick up something from Pascal's triangle so that we bridge the gap, and then, we'll move forward, okay?
Okay.
So a plus b to the power of n, as we just saw, can be written as sigma. This is the sigma notation, where r goes from 0 to n choose r, a to the power of n minus r times b to the power of r. So in the expanded form, you can write like this. So sigma notation, in such a short, space, you have represented this long series. Perfect. That's how it is. Now, can you please read these bullets, which will give you something about the binomial expansion?
Yes. So the number of terms in the expansion of a plus b to the power of n is n plus 1.
Correct.
The degree of the polynomial in the expansion is n.
Correct.
The sum of the exponents of each term in a plus b to the power of n is n.
Correct.
All expansions show a decreasing power of a and an increasing power of b.
Correct.
The coefficients are exactly the numbers in Pascal's triangle.
Perfect. Now here's an example number 7 for you. You need to apply whatever you have learned to expand what is a plus b to the power of 6, correct?
Yeah.
So what I've done here is I've written in the convention of n choose r. So definitely it is 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6 as your coefficients, and the inside terms are a to the power of 6, a to the power of 5 with b, a to the power of 4 b square, a cube b cube, a square b to the power of 4, a b to the power of 5, and b to the power of 6. So when you place them together, you get the expansion for a plus b to the power of 6. And you now know also how to calculate these numbers. You could calculate using the strategies which you have learned, or this time, because it is just 6, make your triangle and go to the row which has 6 in its first diagonal, correct? So those numbers are 1, 6, 15, 20, 15, 6, and 1. Just place those numbers right there and you have your answer. Do you see that?
The one above, the last one.
Yes.
What is that? Why is that like that? Why can't you write it as the one like below it?
You mean this one?
Yeah, but like the one above it, like why is it written like
choose
606.
using the convention. Yeah, because the value, see, what we have is n choose 6 choose 2 is same as 15, correct? So many times
when you go on the grid, on the triangle.
So it is the same correspondence. We're just putting the values. Many times we don't need the numbers. We have to work with the coefficients. So we'll come up with many questions where the question will be, what is the coefficient of the term which has a squared b to the power of 4 in a plus b to the power of 6? You understand the question?
Oh.
So we are only interested in that particular term. What is the coefficient of that? So in that case, this convention helps. We don't have to write the whole series. So
Makes sense.
Different ways in which questions will be shot at you and you have to tackle them. So we have to go with a very broad base, all variety. And that's why I'm introducing you so many conventions, because the question could twist, and very complicated questions can be created on this particular topic.
Yeah, okay.
We have already seen the complicated. It looks simple, right? Elegant. It's very tricky, okay? Now, so you understand this part. Let's go to example number 8, which is, again, kind of similar. Now, can you please read example 8, the question?
Yes. So find the coefficient of each of the following. Okay. So a to the 4, times b to the 8, and write it in the form a plus b to the power of 12.
So in the expansion of a plus b to the power of 12, what is the coefficient? You see, what is the coefficient of the term which has a to the power of 4, b to the power of 8? That is the question. Do you understand?
Right, yeah.
So we're not looking at the whole series now. We're looking at the small part where we have a to the power of 4, b to the power of 8, and we are only looking at the coefficient. So what I've done here, just to explain, is I've also introduced the term which will have this particular coefficient, correct? So the term is, because the power is 12, correct?
Yeah.
And b power is 8. So the coefficient is 12c8.
Why can't we choose the a power, like 12 over 4?
Okay, now let's look at the coefficient. So 0, 1, 2, and this 2 matches with b squared. The a is n minus 2. Do you understand?
Oh.
This 2 matches with b squared, not with a. So you have to.
So it has to be b. Okay.
Yes, it has to be the second term. I mean, a plus b binomial, the b part. Correct?
Got it. Yeah.
If you put a, sometimes you may be correct, because for symmetry you may get the right answer.
Yeah.
In this case, it is correct. 12 minus 8 is 4. 12 minus 8 is 4. So in this case, you'll get the correct answer, but not otherwise. Okay.
It's like when we did to the power of 4, it was a squared, b squared. They're both the same.
That sometimes it works, right?
Okay, yeah, but not always.
It is the b power, right? B. So I just wrote this term, which is not very much required. However, to make you understand, it is 12 choose 8, which we are looking for when we are saying coefficient of a to the power of 4, b to the power of 4 in a plus b whole square. You got the idea. Now you know how to calculate 12 choose 8. So 8 terms are there. 1, 2, 3, 4, 5, 6, 7, 8 numbers multiplied, decreasing from 12 on the top, and 1 to 8 in the denominator. Multiply them and get your answer. Without calculator.
Could you also write that if it was with the calculator? Write 12 times 11 times 10. And then times 9 times 8.
It takes too much of time. Yeah. But many times, without calculator, when they ask answers for these, even this is sufficient.
Okay.
Yeah, they will specify the number also, and they can write this. Okay. Anyway, now see, the question can become tricky. The next part B, can you read this, please?
So p to the 5 in 1 minus p to the power of 11.
Correct. Now in this case, the coefficient is still 11c5, right? So p to the power of 5, because it is 1 and p. So the number 1 is the 1 number, right? So we are given the b part, correct? Now remember, p is with negative sign. Since it is negative sign and the power is 5, correct? So negative power will give you a negative answer, and therefore the coefficient will have a negative answer. So therefore it is important to look into the term to get the right answer. So you cannot simply write n choose r. You get the idea?
Yeah.
You have to see the terms. Now, next one, C. Can you look into that?
X to the power of 4 times y to the power of 12 in 2x minus y to the power of 16.
Yes. Now, what is the answer?
So would y to the power of 12 be that b?
Yes.
Okay, so you do 16 choose 12.
Yes.
Times 2x.
2x to the power of 4, right? Minus y to the power of 12. Do you see that?
Yeah.
So when you open, 2 to the power of 4 will be part of your coefficient.
Oh.
Don't miss that.
Oh, okay, yeah.
But in this case, minus is the even power, so you get positive answer. Minus is even power. Minus y to the power of 12, so that becomes positive.
Positive.
So you have a positive.
So you got, it was 2x to the power of 4 because 2 to the power of 4 is 16.
The expression is x to the power of 4, y to the power of 12. So here we have, but the term is 2x. So in your expansion, you'll have 2x, correct?
Oh, you thought, oh, okay, but people make the mistake of just putting x.
Yes, and not taking.
Got it.
And also, because they see this negative here, they'll write negative, which is wrong. Negative y to the power of 12 makes it positive.
Positive, yeah. Only if it's an odd number, then it'll be negative.
I mean, walk away questions, simple things. Students make mistakes by not paying attention to details. You get the idea? Yeah. Right. This is actually
a lot to think about.
Yeah, simplest question, but I've seen so many, 50% students will make mistake here. Question number 9. Okay, so now we are actually getting back to our Pascal's triangle. So what I did here is that I replaced those T and R's with C and R's. So you see there's just to give you a visual look that actually that Pascal's triangle could be written this way. Now binomial coefficients. You get the idea? And again, thinking about the same diagonals and rows, and that is how we are replacing in our mindset the Pascal's triangle with the combination binomial coefficients triangle, correct? Because they have been used so many times, and you know that it is good to see them together. So this is kind of a innovative thing, just putting them together, right?
Right.
These binomial coefficients have the correspondence with the terms in the Pascal's triangle. The relation is also written as, so you remember that T n r is equal to Tn minus 1 r, Tn minus 1 r minus 1. So I've written that in the coefficients. N choose is n minus 1 choose k minus 1 plus n minus 1 choose k. I've used this same, and that becomes a standard formula for binomial coefficients because they follow the same rules.
Yeah, so same formula, just in a different format.
Correct, same formula. So read NCR as n choose k, and CK as n choose k, right? So here's an example for you, Amy. Can you answer this question? This is a test question.
So if 126 choose 78 equals 125 choose 78 plus A choose B, find A and B.
Correct. So what is A and what is B?
So A would be 125 plus 77.
Perfect, B. That is
not plus. Yeah.
And similarly, we have the next question, example 10. So when I share the video with you, you need to answer these in your notebook, correct? But we have rearranged it, and that is you could have a question in your test. Is that clear to you?
Every time I see if it's like a negative or something, I know it's rearranged.
Rearranged, correct.
Okay.
That's what it is, right? So, and you have to go with the lower number. Only one high number and two lower numbers. That's another way of looking at it. Correct. Next example here is the row symmetry. We had been talking about row symmetry, and we have seen that the numbers same distance away from both the ends are same, correct? And therefore, right, NCK is equals to N choose N minus K, correct?
Yeah.
So we could use, so I choose K, sometimes I move to K and sometimes to R because, you know, when we choose that scientific symbols, by default, they give me NCK. So
okay.
that NCK also comes in, but you know, many times we write K instead of R. Is it okay?
Yeah.
But you could write anything, okay? But these are standard. NCR and NCK are standard. So example 11 is on the same lines which we just did, but slightly different. So now the question for you is, can you read the question and answer?
Yes. So if n choose 9 equals n choose 3, find n.
How will you find n? Tell me.
So k is n, and we need to find n. So you do, okay, wait. So we got 3. So n is, oh, so you do 9 plus 3.
Correct.
Because 12 minus 9 is 3.
Good job. So this is very easy way of looking into it, rather than, you know, solving two simultaneous equations.
Yeah. Oh.
Don't do that. Just add them up, because you are moving from the left side, you are moving from the right side, same position, right? Just add them up, right? So you get the value of n.
That formula helps on the top.
Yes,
yeah,
that formula
makes
helps.
Sense.
Correct. So similarly, based on this formula, we are saying if 20C16 is equals to 20CK, what is K? And K definitely is not 16. K has to be 20 minus
16.
Minus 4. Correct. Done. Got the idea, right? Now here is another very interesting way of looking into a Pascal's triangle. We have seen the triangle so many times, so I thought let me just adjust it. So
right.
Brought all the terms to the left aligned. So when you do left aligned, you have a rows and columns. So we'll now look into these rows and columns and some interesting patterns from here. So what simply is, you know, this portion which we have, you know, if you add them up, you get the number 2. You can straight away add rows and columns. Very easy to do, right?
Yeah.
So just add this row, for example, and you get the number 8. And next row, you get the number 16. So this is showing the sum of all the rows. Do you see a pattern in this? The numbers are 1, 2, 4, 8, 16, 25, 36, 49, 64, 81.
Oh, 2 to the power of n.
Correct, 2 to the power of n. And that is what you get. Correct. It's a... there's a mistake here in timing. It should be 2 to the power of n, that is correct, but these totals are wrong, okay?
I was going to say, where does 25 come?
Yeah, so 25 is, so that is a typing error. I'm sorry for that, right? So, so there are wrong numbers here. I'm sorry. Okay, so these numbers are wrong, but the answer is 2 to the power of n is correct.
The other ones work as well.
Yeah.
Yeah,
so
up to 16, that's right.
Yeah, so they are correct. But here is a typing error. So when you add these rows, you get 2 to the power of n as your answer, and that is what you get here. And also you can see that when you add the numbers 4 and 6, you get the 10. So adding the closest to previous 2 on the row gives you this particular pattern, and there you get. Another thing which we learned is the value of r, and the value of r should be between 0 to n, correct?
N, yeah.
However, if you put r as more than n, what you get is a blank, that means zeros, right? So here is a very important thing to understand, that if I write in NCR convention, 0 CR, so you understand? N should be actually not less than r, right? 0 is less than r for sure, correct?
Yeah.
The answer has to be 0. So these are blank spaces shown in that particular color.
Oh.
So in some calculations, you know, you're just deducting and you come to a stage where it is like n value is less than r. You know you should not be going beyond that because r is restricted, correct?
Right, yeah.
0 and that. But if you do calculations and you do get 0 for n, you know the value is 0. Is that clear to you?
Yeah.
It could be there, but the value is 0. Perfect. And these are the related formulas. NC0 and NCN is always 1, correct? Both are 1. So that is symmetry, which you see both these ones on the left side and on the right side, right? So those are those ones we're talking about. Is that clear to you?
Yeah.
So that is what we're talking about right here. And of course, this is a calculation mistake. You can always fill these values with 2 to the power of n. Is that correct?
Yeah.
Great. Let's move on and look into this table once again. And I know this was being copied from there to this place. So of course, I know this is wrong. So let me erase this off. Now, we'll look into that diagonal sum. Do you see this? So rows and columns. Do you see? You can actually starting with 1, if you start with 1 and then add the numbers, then the sum is always given right as shown here. So next to row column, you find the sum. So if you add from, let's say, 1 to 7, you know the sum is 7 times 8 divided by 2, which is 28. And in this fashion, you can find the answer right from the table. So it gives you the sum of all the elements in the column.
So it's like you go down and then with the sum, and then you like kind of do a bit of like a curve.
Yes.
Down. Okay. Yeah.
So we'll actually name this as a hockey stick property. So it gives you a feel. If you see into the table, triangular table, it looks like a hockey stick. So we call this as a hockey stick property, and then you can easily find the sum at the end of the hockey stick where it turns, right? So this is that hockey stick which you're talking about. Is that clear to you?
Yeah, yeah.
So that is the hockey stick property which we are referring to. Perfect. We'll look into this hockey stick property also. And here is our next question based on hockey stick property, which you just saw. So, Amy, can you read what is written here?
Yes. So explore patterns in the Pascal's triangle. The hockey stick identity. So the sum of elements in a diagonal line starting at 1 is equal to the next element down diagonally in the opposite direction.
This is the important part, in the opposite direction. So when we look into this diagonal, which is moving like southwest, then opposite direction is you leave the diagonal, and then this is your opposite direction. 10 is the sum. Do you get the idea?
Okay, yeah.
If you follow a diagonal from the other side, moving towards southeast, and then opposite direction is don't go there, but go in the opposite direction, you find the sum there. Do you get the idea?
Right. Yeah.
But you know, when you try to write this property in terms of NCR, then the sum is placed at a position where in the first case, in this particular case, you're moving along the diagonal number increases. Do you see that? You move to the next diagonal, the sum is placed, and the row number also increases. Do you see that?
Yeah.
Okay. In this case, when you end at this particular diagonal, the diagonal number did not increase.
Right.
You are on the same diagonal. The row number increases. So that means there is a different answer.
Yeah.
On how do you move? So that is critical. And that's why we have example 13 here. And can you read this example and the answer and justify the answer, please?
Yes. So T44 plus T54 plus T64 plus T74 equals T85.
So in which direction are we moving? T44 is the end point, right? You were at the end, somewhere there at the end, correct? So,
yeah.
Fourth row end. So that is this diagonal, green diagonal. Do you see that green diagonal? T44.
Yeah.
T54, you move down, but in the same diagonal. So the end point 4 is the same diagonal. Do you understand?
Yeah, because we're
diagonal 4.
Okay, yeah.
And the sum will now land in the diagonal 5th and the next row. So 7 is the position where you want to stop. So the next row is 8. So T85 is your answer.
Yeah. Yeah. Got it.
Now see the other pattern.
So 5 choose 0 plus 6 choose 1 plus 7 choose 8 equals 8 choose 2.
Do you see that? 2 and 2 matches. Means it is movement which is this direction, correct? And we are still on the same diagonal where the last point was. However, the row will increase as we are going down.
Yeah. Makes sense.
This is very important. So if your diagonal numbers are increasing, stay on the same diagonal for this sum. If your diagonal numbers are not increasing, increase the diagonal number for your result.
Oh, okay.
And I've also used both nomenclatures, the Pascal's way of writing and the binomial way of writing, because this is common to both the chapters.
So what you're saying is, when it comes to the hockey stick identity, the last element that you're on, it's basically the same diagonal, just the row, like the next row.
Yes.
Okay. Yeah.
It is the same diagonal only if you are maintaining the same you know.
Yeah.
You're moving southeast.
Yeah.
Correct. So if you have been if you are changing the diagonal number, then you don't change at the end.
Right, yeah.
But you are staying in the same diagonal all the time, then you change at the end.
Then you change at the end.
Like this. You can
Yeah.
So make a rule for yourself so that you could answer questions like this. So we have this question. Can you tell me the answer? What is A and B in this case?
Okay, so should I read it or just answer?
Answer.
Oh, okay. So since it's all going up the rows, so it'll be 14A. So A would be 14, and it's all on 10, the diagonal, but we're doing the hockey stick thing, so it has to be to 11.
Perfect. That is how you got to answer.
Oh, okay.
Clear to you. Perfect.
Yeah.
And now here is examination question, example 15. Can you read an answer?
Okay, so write an expression for the sum of natural numbers from this hockey stick identity.
I'll keep this as a homework for you. So natural numbers are in diagonal 1, and you're moving in this particular direction. Therefore, the sum will always be in diagonal 2, correct? And one number more, so we get n plus 1. Do you get the idea?
Oh, yeah, because the natural number's in diagonal 1. We have to find the answer in diagonal 2. Okay, yeah.
And wherever you end, increase the row number.
n plus 1.
Done. So you don't have to do, you'll learn so many methods of adding the natural numbers in different ways and finding the answer. And from hockey stick property, it's straightforward.
Oh.
That's the beauty of Pascal's triangle. It makes things so simple, unbelievable.
It's amazing.
It's like kids' game. They will answer so many brilliant questions just looking at this, right?
Yeah.
Okay. Now, we are looking into another property of Pascal's triangle, which is called row sum property, right? Where I did a mistake in typing. So row sum property is when you add the numbers in a row, you get 2 to the power of n as your answer, right? So here is a tricky question. Example 16. Can you please read the question and answer it?
Okay, so find the sum of all its terms in row 15 of Pascal's triangle. 15.
N equals to 15.
N equals to 15.
What is the answer?
So in Pascal's triangle,
yes,
it would be 1 less?
No.
1 more?
Same.
Oh.
So let's be very clear. Find the sum of all the terms in row 15th of Pascal's triangle where n equals to 15. I'm also writing n equals to 15 for you. So nth row in Pascal's triangle sum is 2 to the power of n. You get the idea?
Yeah.
So if the row is 1, then the sum is 2. 2 to the power of 1. If the row is 3, then the sum is 8.
Yeah.
So now, if this question is asked in Pascal's triangle chapter, correct? And we are specifically referring it here, then the row of Pascals will be considered as 15 only.
Oh, okay.
But if I ask this question saying, what is the sum of elements in the 15th row of Pascal's triangle? Now, I am not in this chapter because I'm just asking you a question at the end of the unit.
So that's
then
1, 2, 3, 4.
You have to change and adjust. Do you get my idea?
Okay.
That is the key part. Now,
perspective is hard.
Question number 17, please. Can you read and answer?
So, which row of Pascal's triangle has the sum of all its terms equal to 4096?
Correct. Since we are in Pascal's triangle, we'll specifically be in Pascal's triangle and use this formula. Is that clear to you?
Okay, yeah.
Now, the idea here is 2 to the power of n is 4096.
Yeah.
Many times it is difficult to solve this because you have to use logarithms, correct? Do you remember?
Yeah.
Log both sides.
Let me just get my calculator. You do log 2 of 4096. 12.
Correct.
Yeah? Okay.
So that
I can't do that in my head.
You have to revise logarithms to get into this. And now we'll quickly go through a few interesting properties to end this particular chapter. Another, give me 5 minutes, okay? Now here we are talking about sum of entries with alternate sign. For example, we had an example there. Instead of a plus b, if I have a minus b, then the powers of b will be negative, and that will result into alternating negative signs, correct? So as you can see here in this particular diagonal, which is diagonal 1, we have everything negative, diagonal 3 and 5, and so on. The odd number of diagonals will give you negative signs, correct? Now in this particular case, and combining our knowledge about symmetry of the numbers in the Pascal's triangle from left side and the right side, if I now add all the numbers in a particular row, what do I expect? The sum should be always 0, right? Sum will be always 0 when I have a series in which we have alternating negative numbers. Clear?
Yeah.
Except for the first one. Because in the first one, there is only one element and the sum will be 1, not 0. So be careful. In an objective type multiple choice question, if they say it is 0 for all, it is wrong statement. Because if we have only one row, then the sum is 1.
Right. Yeah.
If n is not equal to 0, that means n is 1, 2, 3, 4 in Pascal's triangle, then it is sum is 0. But if n is 0, 0th row, or there is only one row, in that case, the first row, in that case, the sum is 1. Okay? So you have to be careful about this part, how the question has been framed and how you need to answer. So,
how would that question be framed? Would they say how would they use the word alternate signs, or would we have to do
true or
it?
false? No, it is true or false. The statement is true or false. If you expand a minus b to the power of n, the sum of coefficients will always be 0. True or false?
Oh, okay.
Then you will say it is false. If n is 0, then the sum is 1.
Yeah, if n is 0, the sum is 1. But if n is not 0,
it is 0.
It is 0. Okay, yeah, got it.
So they could frame this a minus b to the power of n, and they're not giving any value for n, right? They're not writing whether n is 0 or not. Then you have to say it is false because n can be 0. In that case, the sum is 1.
Oh, yeah. Because that would be that top one.
Top one.
Yeah.
That's the whole thing.
Yeah.
So we can trick you at so many places. Now another beautiful identity here, sum of first n natural numbers, which we talked about, correct? So here it is. I'm giving you the answer which we just saw also. Sum of first natural number is n plus 1 choose 2, correct?
Yeah.
So you move on to the next diagonal and the next row. And sum of 7 will be how much? Well, you can just plug it in here. 8 choose 2, which is 28 is your answer. So that is how you could easily find sum of natural numbers, right? So the question here is, sum of first 100 natural numbers is what for you? Well, clearly 101 choose 2 is your answer, and you can use the factorial form or the shortcut method which we understood, and you get your answer as 50-50. Okay? So these could also be, without calculator, you have to find this answer. Is that clear to you?
Yeah.
So you can easily find this question answers, and you could use the formula if the numbers are bigger, right? Sometimes you may use. But how? When we're talking about the choose 2, I mean, n choose 2, if you have to multiply numbers and divide by 2, n times plus 1 divided by 2 is also the formula which you know about. Correct. The last identity which I thought I'll show you once again here, which we were looking for some square numbers. So I again place this sideways. So you can observe that the sum of elements in the third diagonal, which is diagonal number 2 for Pascal's triangle, always gives you a perfect square. 3 plus 6 is 9, 10 plus 15 is, and so on, is a perfect square. And that gives you a formula in a way. That is n square is equals to n choose 2 plus n plus 1 choose 2. Do you see that?
Yeah.
Second diagonal. So that is choose 2, and you move the row and n plus 1. Do you see that? And what you do is you get n squared, and definitely n has to be more than 1 in this particular case. And then you get all these results, correct?
Mm-hmm.
That is how we get this particular relation also. So the relation is so simple. What is, and you may be given a question which is saying, what is the value for 7 choose 2 plus 8 choose 2? That is a simple question, but so difficult. And you will not even imagine this 7 square is the answer. You get my point? So look at it very carefully. It is an examination question. Coming out from such a simple thing. Yeah.
So the diagonal would obviously stay the same because we're in diagonal 2 of Pascals.
Picking up the two numbers, picking up the two numbers and adding them. Now, based on this, here we have the examination question, as I was saying. So see here, we kind of have a series here, which is n choose k whole square. So we are adding these squares, and the combination answer is 2n choose n, and that is the result, right? So you could actually derive this particular formula, but now we are given the formula, and here is a question for you. Show that the sum of all the numbers, 3 choose k whole square, is 2 times 3 choose 3. What I'm trying to do here is third k is from 0 to 3. That means we're looking into the third row. So the numbers in the third row, when you square them up and then add, then you get the same number, which is at 2 times 3 is 6. 6 choose 3, which is right there. So you need to verify this result. So you can do that by literally adding these numbers, correct? You get 20, and the number here you can read as 20. Do you see that? It verifies our formula.
Right.
Got it? Correct? It verifies the formula. Very important formula which you can make note of. And here is your examination question. Can you answer this question for me? Read and answer.
Okay. So evaluate 9 choose 2 plus 10 choose 2.
Correct. What is this?
So the diagonals are the same.
Yes.
So it would have to be, so 9 choose 2.
10 choose 2. What is this equal to?
Okay, wait. I mean, I can do it off the triangle. I'm trying to do the method that we just did.
Yeah.
Should I do it off the triangle or the method we just did?
As you wish.
Okay, so off the triangle, it won't be, you don't add them.
Yeah.
No, I don't know.
Squares. We're talking about choosing these two elements in the same diagonal, right? We are moving the row. And what you get is n squared. That is what we are looking into. Do you get the idea? So things may look simple, but when they come, when you combine all the things that you learn, and that's what happens, right? Too many things. So you need to put them one after the other and make some formulas. And so now we know this is a perfect square, and the result should be 9 square. You get the idea? So it is 9 square, which is 81. So we're talking about this. And of course, we have gone beyond this, right? So 9 and 10, so we are adding these two elements.
Oh.
And when you add them up, you get 81 as your answer. You get the idea?
Yeah. I just forgot about that. Okay, yeah.
Yeah, so there are too many things. That's what the patterns, there are so many patterns we have talked about today. And therefore, it is confusing. And it is interesting, though. So once you put them in order, you will be fine. So these test questions which I placed, they are real examination questions. May look very simple now. Imagine when they are, after a week, somebody's asking you this, right? Okay. So we'll just take 2 more examples to end our lesson today. So now we have sum of squares, which we just learned, right, in the previous slide. Example 21. Can you please read the question for me now?
So determine the sum of squares of the 6th row of the Pascal's triangle. Note that the 6th row of Pascal's triangle is n equals to 5.
Correct. Now answer. Determine the sum of squares. So we are using n equals to 5 using this particular formula right in the top. So 2 times 5, 2n, right? 2n row. And the element will be 5 itself. 2 and 5 will give me the answer. So when you calculate 2 and 5, you get 252 as your answer. You get the answer. So that is how you're going to answer. And here is another examination question, which is 2 times, and within bracket, we have the squares of these coefficients, which is 6 choose 0, 6 choose 1, 6 choose 2. All 3 are squares plus 6 choose 3 whole square. You need to evaluate this particular expression. So how will you do it? So that is another question for you to do and try at the end of the video. Is that clear to you?
Would you just use that formula though?
Yes. See, 2 times. So you have to. So you can make a. You know now that you are holding on to the whole row, right? Because the symmetry, we have odd number of elements. So these are duplicated, correct? These are duplicated.
Yeah.
And so we know the whole square. So 2n times, right?
Yeah.
2 times 6 is 12. So we know 12, 6, see, 12 choose 6 will be your answer. Is that clear?
12 choose 6, yeah.
You get the idea, right?
Yeah.
Choose
3 times
your answer for this particular question. Now, to end this lesson, I'm also sharing with you one more very important pattern which has been recently discovered. So this is called the Star of David theorem, discovered by Henry W. Cloud in 1972, right? So recent. And the pattern seen was that if you pick up any particular element anywhere, right? Let's say we have an element 5 here. In that case, you can form a star with 3. One triangle, like you understand what we mean by a star kind of thing?
Yeah.
The star will be one triangle like this and the other triangle kind of like this, correct? If you make a star pattern, in that case, you will notice that the product of elements in these is same as the product of elements in those. That is what star pattern is. So you can try it out. Patterns and very interesting. And as I've shown here, 35 times 15 times 56 is same as 20 times 70 times 21. The shaded green and shaded orange, their product is exactly same. And that is the star pattern which you can explore. Now, based on the star pattern, we could have many questions. And as you can see the star pattern right there in that Pascal's triangle. So what we're doing here, Amy, is that we have selected one element, 35, and taken all around, there will be 6 elements, correct? That is how you form a star. So I'm trying to show you how this star is actually formed, and it's formed like this. So you have all around 6 elements always in this hexagon. Now, you can choose the 3 alternating, multiply them with the other 3 alternating, you will get the same product.
Oh, okay. And that works throughout the whole triangle. Like if you find 6, okay.
Explore. And then, for example, I just took one particular thing, which is 7C4 is shaded as 35. And these elements are referred to now in the Pascal's triangle nomenclature. With binomial coefficients. You can write this as a NCR or TNR, any way you figure out, right? So when you do this, you can come out with this relation that in this particular case, these positions are as mentioned here. And so this product is same as that product. Is that clear to you?
Yeah.
So what I've done here is actually given you a formula, which is very interesting. And so basically, for any general position NCR in between, which I've written as NCK in this particular case, this product, which are the alternating, you understand, positions around that hexagon, right, which is formed, is equal to the other product. But in terms of the convention of N choose R, it is written like this, which is slightly confusing at the moment. But actually, when you see it more carefully and practice some questions from your book, it will make a lot more sense to you.
Perfect. Okay. Yeah.
I think this is where we are going to end today. And this is a beautiful, beautiful discovery and interesting pattern to watch. So many things, as you can see, are still developing from this simple pattern. So, I mean, how do you find today's lesson and what do you think you learned today?
Oh, well, I learned a lot for starters. This topic was obviously brand new to me. So still getting used to some of the new terms that I'm learning and all the different like alternate strategies to get to different answers. There's obviously multiple ways of getting to answers because like you said, if it's a calculated test, then obviously we can simply use the factorial notation formula because you can plug it into the calculator. But when you don't have the calculator, you said you come up with a name for that other one where you just you take that term and then you do like 9/1 and then 8/2. Like that, multiply. Then I learned new different ways of writing it. So you said obviously globally it would be in the bracket form, the NCR. You can it's kind of N choose R, yeah.
CNR, CNR.
Yeah, that's
CNR.
CNR, yeah. So those were the different forms. Then I learned, what else? There was the hockey stick identity one, which is very good. So instead of like going back and just doing all the adding each term, you can simply just look at the, let's say, the diagonal and go in the opposite direction of what the diagonal was going in. Make sure, this is the bit where I found a little bit tricky, but I guess I'll get my head around it when I start doing questions. But it's more about like the perspective. So if you're talking about Pascal's triangle and you know that's the topic and they're referring to the certain row of that triangle, then you know the rows will be going from 0, 1, 2, 3, 4. Good. But if it's from an outside perspective, just saying the 15th row of Pascal's triangle like that, you count the rows as 1, 2, 3, 4, like binomial expansions and things.
N plus 1 will be your answer, yes.
Yeah, N plus 1. Okay. And then binomial expansions. So I found that really cool. So like if it's just a plus b to the power of n, you can simply expand any of them because the Pascal triangle, those values that are in the triangle are the leading coefficients for all the expansion of it. So that's really helpful. And then we learn the sum of the rows is 2 to the power of n.
Correct.
And then we learn there's a symmetry in between because it's like reflective, the left-hand side and the right-hand side. If it's even number, you get that repeated in the middle. If it's odd, it's just simply a reflection. We had the triangle numbers, which were in diagonal 2 of like Pascal's triangle.
Good job.
Thing. Then we had the tetrahedral. Is that how you say it?
Tetrahedrals 4.
Tetrahedrals. That was in 4. But in Pascal's triangle would be 3.
And it works for all the numbers. If you put 5 things and then go up, the count is there in that diagonal, right?
Right, yeah.
So it's very, very interesting. So, Amy, that was pretty nice. We actually summarized a lot of things and I'm glad you remember so many things. Now, it is time for you to practice some questions from your book. Yeah. You must have seen that I've actually merged a lot of concepts from the chapter which we are going to learn tomorrow, combination, binomial theorem and all. And because they go hand in hand, and many times it is easier to do questions based on binomial theorem if you pick up from the Pascal's triangle. And I also use the conventions, which we, variety of conventions, so that any book you pick up, any test paper or any examination paper, you will not get confused about it. You will understand what they're talking about, right? That's the whole idea. So with this, let's take a break here. And hope you grasp everything, and whatever you don't understand or find difficult with, share with me. I'll try to answer those things. And in the next lesson, we will take up binomial theorem and see how to work with binomial coefficients along with Pascal's triangle terms. Okay?
I just feel like, if I start doing questions and things, I'll get the gist of it. So I'll let you know how it goes. Sure. Thank you so much, sir. Thanks. I really appreciate it.
Bye.
Have a good rest of your day.
You too. Thank you.
Thank you.